start the recording. And before, we start the class. So how was the quiz? Was it okay? Was it easy? Did you find anything difficult, or yeah, anything you want to share about the quiz? Yes, anything? Or was it too easy? Uh, okay, so we'll get back to the quiz maybe later on, but we have to, like, we have a lot on the agenda, inshallah, for today and for this week. So the last time, we talked about was about the dodecahedron, which had 12 sides, and you can see here that there are 12 constraints. So there are 12 constraints, and there are like okay, let me. All right. So okay, excuse me. So we have this three you can say dimensions as the domain, but for the range we have got 12 different constraints. And I mean, the main thing is, as more and more constraints, they are active, right? Or you can say they are binding. So what will happen for this particular figure? What will happen if, for example, one constraint is active, or if, let's say, two constraints are active? So what will happen? So I want to hear from you, what would be the impact if one constraint is, let's say, binding. And what is binding, by the way? What is a binding constraint? When, how to check a particular point is binding or a constraint? How to do that? Just we have to plug the point, right? So we have to plug the point, and what is binding? What value we should get for a binding constraint? Anyone? What value is required for, in order to be considered as a binding constraint? What we should do? No one remembers? So if we get a value equal to 0, right, we call it as binding or active. And if we get a value which is less than 0, right, then we say that this is non-binding. So, and we can say it's not active, right? So we just say this, that either it is binding or not, or it is active or not, right? And in this case, yes, do you remember, like, what would happen if, for example, more and more constraints are active? So where we would move? You remember? What would be the trajectory? Uh, yes, anyone remembers? If more constraints are active, what would happen? We would move from, you can say, the face. Like, I will move from the face, to an edge, to a vertex. So this will be your impact, that if, for example, only one constraint is active, I may be, the point may be here on the face, right? Because if it's on the face, still, it is considered as being on the boundary. But if more constraints are active, then the point may be on the edge or maybe on the vertex, right? So let's see here that, I mean, if, for example, all the constraints are not active, right? So we write it like this. That means the h of x. So overall, h of x, and the point is x steric. So at this point, uh, like all the constraints, they are not active. So we are getting the value less than 0. So we say that the active set. This is, by the way, representing the active set. So the active set is null, right? So we can say this is in the interior. But if, for example, the active set is non-null, so obviously for all these three options, these are considered as not interior to the surface, but on the boundary. So here we are on the boundary, on the boundary, on the boundary. But if only one constraint is active, so this means it is on the face, the outer face, right? But not on the edge or the vertex. But if, for example, two are binding, then that would be enough to put it on an edge. But if, for example, there are three constraints which are binding, then we'll make it, you can say, this will put it on the vertex of this dodecahedron, right? So okay, let's look at this thing that yeah, I mean, the main thing is we have, yeah, sometimes some of the binding constraints. So it always, in reality, some constraints are mostly binding and some constraints are non-binding. So it is rare that, for example, all of the constraints are binding. It's very rare. So most of the time, let's say we have got 4 or 5 constraints. So some constraints would be binding and some constraints would be non-binding, right? Uh, and the thing is, there are some optimization software like different which are available in the market. So which deal directly with the double side functional inequalities. Double side functional inequality means that here for h of x, we are not only giving the lower limit, this is the lower limit, but also we are going the upper limit. So we are not writing it in this form that, for example, h of x is less than equal to 0. So we are not writing like that, right? So we are not just saying that, for example, h of x is less than 0, but rather, in reality, we have to, or we can give the lower limit and the upper limit. And similarly for the variables, the upper limit and the lower limit. Like, for example, the Desmos also allows you to, put or to use double-sided inequalities on the variables, because we can, say that x ranges from, let's say, -10 to +10, right? So in this case, I mean, we can, some software, they have got this, you can say, capability. But the thing is, why we use h of x is less than 0 is just, you can say, for the sake of simplicity, to make the things easier, right? And so in this case, I mean, this is, you can say, more for the notational simplicity, right? So just to keep the thing simple, we do this. But I mean, otherwise, this is more straightforward. This is more straightforward. This is more what you have seen before. Like, you just put the upper limit and the lower limit, and that's it, right? So if, for example, the software has got the capability, then it's a good idea to write it in this form. That means for the constraint as well as for the variable, you give the lower limit and the upper limit, and that's it, right? Okay, so there are like many case studies. The ones we would study is, this one, but later on. And then we can also try, this one as well, because the pattern classification, this is, directly in computer science, right? So this is more like AI. Okay. So, but for the other one, you can say they are more like towards, and also this least absolute value data fitting. So, but these, we keep them for a bit later on. So the thing is, for very small problems, or very, you can say, simple problems, just by looking at the diagram, we can find the minimum and the minimizer. So can anyone tell me what is the difference between a minimum and minimizer? So what is the difference between the two, minimum and the minimizer? So can't hear from you. Yes, just the difference between the minimum and the minimizer. What is the difference? Yeah, but
Minimizer
what
is
is,
the point.
yeah, the minimizer is the point, right? So minimizer is the point where the function attains the minimum value, right? So I've written. So minimizer is the point where the function gets the minimum value. So the minimum is the function value, and the minimizer is the point which will give us the minimum function value. So f of x, the value of f of x. For example, the value of f of x is, let's say, minus 10. So it is minus 10, this is the minimum, but it is minus 10 at what point, right? So that point is known as the minimizer. Now, obviously, you can, you have seen that, for complex problems, just see, if we have, for example, 2 dimensions or 3 dimensions, okay, we can, uh, make a graph, we can find the minimizer directly. But if the dimensions increase, so 3, 4, 5, 6, 10, and nowadays, we have this big data concept, right? Big data. So in big data, the things are now going to, millions of dimensions. Very easily, we can have millions of dimensions because we have got, network data, and some other kind of data, and things are, you can say, things have really changed. So in that case, obviously, we can't make any, you can say, graph for that. It's very, very complex, and we cannot, like, display that. So the we have to, like, do away with the geometry, right? And in that case, we have to come up with the mathematical things, right? And you can say different algorithms are there, but we cannot, obviously, show the geometry. Even if, we have got like 4 or 5 dimensions, things really become, different, to a different level. But in, big data era, we have got, we can get easily, you can say, uh, hundreds and thousands and even millions of dimensions. So the next topic, it's, a different topic, slightly different, but it is obviously related with the, minimum. And we have, a different thing here, which is the, we call it as infimum. So infimum, this word is taken from 2 words, which is infinity, and the minimum, right? So we get infimum. So the infinity, it's from the infinity, right? The first part from the infinity and the last part from the minimum. So what is this, infimum is, and why we need it? The first thing is, what is the reason for that? So for all the problems which do not have a minimum, so which do not have a minimum, that means, okay, just a second. Okay, sorry for the delay. Right, right. So we have this, all of these problems, which we will see. By the way, we will see 5 problems here, and we'll see if there is, let's say, sometimes difficult to find minimum, or the minimum is not there. So still, we can get something, you can say, out of that, and we'll see, I mean, what is infimum. So if we look at, the beginning, it's like the same, that we have got a feasible set, which is a part of Rn. So n dimensions, and we have got a function which is from the feasible set, and the value is, or the range is, set of real numbers. So the function value could be anything: 2.4, 2.55, -3, whatever. So infimum is defined as, or written as, inf. Inf stands for the infimum. And what is the infimum? It is defined by these things. So if the problem is bounded below, right? So that means if we know that the minimum bound is there, somehow we know this is the minimum bound, so that particular minimum bound will be termed as the infimum, right? So that means, for example, if we have a problem and it is bounded, so if the problem is bounded below, I mean, we know the lower limit of the function, then that particular limit would be termed as the infimum, right? So these things will be clear with the examples. But okay, next thing is, if the problem is unbounded below, the easiest example for the second case is this line: f of x is equal to x. So you will get a line, with a 45-degree, right? So in this case, I mean, if I ask you what is the minimum, so what is the minimum? Do you know, for this line? What is the minimum?
No,
Anyone?
it's infinite.
It's infinity, yeah. So the minus infinity, right? Because there is a minus infinity here and there is a plus infinity here. So if you ask what is, I mean, if you ask what is the minimum, so the thing is, there is no minimum, right? You cannot, because it's not defined. So you don't know the exact thing. So we say that the minimum is, like, this function is unbounded. I mean, we do not know what is the lower most value. So in this case, we can say, formally, that the infimum is minus infinity. So the infimum is minus infinity. But if you say exactly what is the minimum function value, so you cannot say for exact that what is the minimum function value, right? So we say that, okay, the infimum is minus infinity, right? Similarly, this thing will come later on, but let's write it now. So just to see the other side of the coin, the other side of the coin is, related to the maximization problem. So for the maximization problem, we have got a similar concept, but we would call it supremum. Supremum, why? Because, you can say this is coming from the word supreme and maximum. If you kind of combine these, so you will get something which we call as supremum. So in this case, for example, if you look at this function again, so if I ask you what is the maximum, so you can't give the value, right? But the supremum would be, what would be the supremum for this f of x is equal to x?
Infinite.
Supremum, sorry,
Infinite.
yeah, plus infinity, right? So plus infinity,
Yes.
or
Plus.
if it is understood, then we do not need to write plus here. But okay, that is, you can say, a little bit later on. But for here, yeah, this thing is important, that if the minimum, or finding the minimum, is infeasible, sometimes we will see, the function is, you can say, ill defined. The function is not defined properly, and somehow you cannot find the minimum, right? Or we have got some kind of, I mean, a constraint clash or something like that, but you can say that the minimum is infeasible, you can't find the minimum. So in that case, what we do is, just remember that we do kind of a flip, and from minus infinity, because we are dealing here with the infimum, we are dealing with a minimization problem, from minus infinity we go to the plus infinity. So in that case, this is very interesting, because in this case, even the infimum is still defined. The infimum is still defined, and we write it plus infinity. So this is a way also, that if the infimum value is plus infinity, So this is, you can say, kind of a, a marker or kind of something. We can know that if the infimum is infinity, that means for sure, finding the minimum is infeasible for this problem, right? So this is, the infimum, just, it's written here, the normal English, that it is equal to the minimum if it exists. So if there is a minimum, then no problem. The infimum and the minimum, they are the same. But infimum helps us where, for example, where there is no minimum. If there is no minimum at all, then just, we can say infimum will be plus infinity, right? So let's look at the examples to see, what we get here. So the first example is, as we mentioned, f of x is equal to x. So in this case, by the way, we cannot find any f steric such that f steric is less than equal to f of x. This means simply that we cannot find a value of the function which is like less than all other values. If you say, for example, minus 1 billion, right? Still, okay, minus 2 billion is smaller value. So you cannot find, you cannot give me a value, a definite value, which is like the lowest possible function value. You can't say that, right? So we can say that the minimum is unbounded below. So there is, no bound. There is no bound, and it's kind of, okay, sorry for that. So there is no bound, right? So this line, it goes till minus infinity. So in this case, we can simply say that the infimum is minus infinity, right? So inf, which stands for the infimum, we can say this is minus infinity, right? So this one was, you can say one of the cases. There are three cases. So we will have, one example at least for all the three cases. So let's look at some other example, right? Which will cover some
Question,
other.
Doctor.
Yes, please.
Can we go back to the definition?
Yeah.
Why is infimum defined for the first one? When there's a bound.
Yeah, that's a very good question. And the reason is, you can say just to encompass everything, because otherwise, just to make sure that this, because you can say most of the time, you can say, or you can say, yeah, many functions, we would get, a lower bound. So in that case, just to, because otherwise that means, we would be needing the minimum and the infimum, two things. So just to keep the thing simpler, right? So in this case, this is kind of, the base case. You can consider it as a base case, something like that, right? Because if you, for example, I remove the minimum, then that would mean that, I would need the definition of infimum and I would need the definition of minimum as well. But by including this case, the good thing is, if, for example, we know that the function is bounded below by something, and there is, reason, there is a good reason for that. We will see the second example that would clarify, that what is happening, why we need the first one. So it will be, because it is bounded below. But we'll see, this example is very interesting. So let's just wait for this example. Now this is, again, a unconstrained problem. So it's the simplest problem. There is no constraint. So this is, f of x equals to, so we are trying to find minimum, and the f of x is x, uh, okay, it's x. So what is this x? Do you know? It is just like, the value e, exponent, right? So this is e raised to power x. So in this case, what happens is, this is very interesting, because the function, uh, as you can say the value of x increases. As the value of x increases, the f of x also increases. But as the x decreases, right, the f of x decreases as well. But the thing is, it will approach 0, but it will not equal 0. So in this case, I mean, if you look at the minimum, can you tell me, is it 0? The function value, the minimum function value, is it 0? Can you say the minimum?
No.
We can't say, because it will approach 0, but it will not be exactly 0. I mean, for example, it can be like 0.000001, but having a value 0, it's not possible. So if you look at this problem, I mean, I ask you, can you find the minimum? So the answer will be no, we can't find the minimum. So, but the thing is, the infimum, yes, we can find, because this value, the function value, it approaches 0. So if it approaches 0, this means this is the first case, and we can consider that the infimum is 0, right? So that's why it is saying that the problem has no minimum. And the problem has no minimum, that means there is no minimizer as well, right? Because the two are related. So there is no minimum, there is no minimizer, but the infimum is possible. The infimum is possible. So the infimum helps when we cannot find the minimum. So we cannot find the minimum, and then there are three different cases, right? So this is like here case 1, because here the value of the function would approach 0, but it won't be 0, right? So let's look at another example. Let's look at another example, and this is again, by the way, the same function. So just to tell you that the same things, could be because of the constraint, things becomes different. So let's say, I mean, we have got a function, very simple, r to r. That means set of real numbers, two set of real numbers. We have got f of x is equal to x, and the feasible set here. So we are only, changing the feasible set. So the feasible set, now it is written in this form, that x belongs to the set of real numbers such that x is greater than 0. So here the thing is, we are saying greater than 0. We are not saying greater than or equal to 0, right? We are not saying this. So we have removed the equal to. So in this case, again, we'll see things are now difficult. Why? Because that means, I mean, f of x is equal to x. So once x is, let's say, 10, we will get f of x is equal to the same value. So the minimum value would be, can you find the minimum? So here, I mean, in this problem, can you find the minimum? Our f of x is equal to x, and x is greater than 0. So the minimum possible
It
value
can
of the function
be,
would be,
well, it can go to like 1 and or like 0.5 or less.
yes, exactly,
So like the
0.5,
other
and
one approaches 0 but is not 0.
exactly. So in this case, still, I mean, if you ask me, I mean, can we find the minimum? So we can't find the minimum, we can't find the minimizer, but the infimum is there. So the infimum, it you can say captures the problem, right? And it helps us really to understand. So the thing is, f of x would, because this will again, uh, we can see, that f of x will be greater than equal to 0, but equal to 0 will be out of question, right? Will be out of question, uh, because there is no x steric such that f of x steric is equal to 0, because this is always greater than 0. This is not greater than or equal to 0. So in this case, we can say the problem is bounded. Yes, we know the lower bound, it is 0, but there is no minimum. If there is no minimum, there is no minimizer. So the infimum will be 0, right? The infimum will be 0. But if you ask me what is the minimum, so it's not possible. Here again, So this one is, like graphical description. You can see as f of x decreases, so we get a smaller value of the function. Here, we have got the smaller, the function value here, and here, we have got the x. So as x, decreases from, let's say, 4, we are getting a function value smaller and smaller and smaller. And as we approach 0, now here you can also zoom this, right? So to just see this point, is, with a, it's not filled, it's an empty circle. Empty circle means that this point is not included. Like if you look at this point f of x, uh, where x is equal to 0, this point is not included. So all other points on the right, all other points like 0.0001, for example, right, all points here, they are included, but I mean exactly this point is not included, right? Just to you can say draw it in an efficient way, so we write it like that. Okay, so here, I mean, it's again said that the problem has no minimum because the feasible set is defined by a strict inequality, and the circle indicates that this point is not included. So this point is excluded. I mean, if you look at this graph and we ask you whether this graph includes x is equal to 0, so your answer should be no, because of this, uh, you can say empty circle. If it is something like, a filled circle, so in that case, that particular point is included, right? That particular point is included. So we can say that, points to the right of x equal to 0, like here, and so they're all included. Like if you have point 0.00001, whatever, right? So that is included, but x equals to 0, that is not included. So again, in this problem as well, we know the lower limit. The lower limit is 0, right? So the infimum we know, but the minimum we don't know. So let's look at another example. And this one, we try to see the last case, where we had some issues. So we call this as inconsistent constraints. Inconsistent means obviously that, the constraints are not consistent with one another. Some, like let's say there are 2 or 3 constraints. One constraint is giving us a different picture. The other constraint is giving us a different picture. So we have got, for example, f of x, set of real number to set of real numbers, and we say the feasible set is defined, uh, so x belongs to R such that gx is equal to 0. As soon as you see this gx is equal to 0, that means this is uh, equality constraint. So this is like now a constraint problem, and you can see, okay, you can see here that G is set of real numbers to R2. So 2 means that there are 2 equations. Now, if you see, you have got G1 of x and G2 of x, and if you equate them to 0, what would happen? I mean, the first one would tell you that x equals to -1, and the second one is telling you that x is equal to 1. So this is not possible. That, I mean, the value of x can be -1 and it can be +1 at the same time. So it is not possible at all, right? So in this case, this is what we say, that there are no feasible solutions, because these two constraints, they are like, inconsistent with one another. They are not consistent. So we can say that the feasible set would be null. The feasible set would be null because we cannot find of any point, right, which satisfies both of the constraints, because all of the constraints, they must be satisfied, right? They have to be satisfied. So in this case, we can say that there are no feasible values of the feasible set, there are no feasible values of x, and again, there is no minimum. But because of this inconsistency, I mean, the infimum is still possible, and this is the case 3, right? The infimum, we can just write it as infinity. Infinity, vice versa. Like we can see that if we have got, I mean, the infimum as infinity, so this is an indication that the function was, or you can say the constraints were, for example, inconsistent, right? So they were not consistent with one another. So this is the third case. and the problem is infeasible. You can say that the problem of finding the minimum is infeasible, but still, the infimum is there for our rescue. Okay, so we can find the infimum still in this situation. So let's complete the examples, and this one is very interesting. Another one, we call this as discontinuous objective. So objective is f of x, and discontinuous means that there is some kind of a gap. So how the gap occurs? So if you look at, the original one, so the feasible set is x greater than equal to 0, and we have a function which is the set feasible set to the set of real numbers, and we say f of x is x if x is not equal to 0, and f of x is equal to 1 if x equals to 0. So if you look at, so you have to see this, from different views. So one view is here, and one view is here. Okay. So if you look at this view, that f of x is equal to x if x is not equal to 0, this is very simple. This is very simple because f of x is equal to x means, we will have like same thing, and we will see this. If x is not equal to 0, so I will get this kind of a line, and I will put a empty circle here. I will put an empty circle because the f of x is, x is equal to 0, this is not included. X is equal to 0 is not included. All the points to the right, they are included. So I will get something like this, this line. Now, how to see the first one? F of x is equal to 1 if x is equal to 0. So for this one, we can indicate that once x equals to 0, so f of x is equal to 1. So we can say, for example, this is 1 and this is 0. So we will see this graph, by the way, in the next, and we just to put it to perspective, we can make a filled circle. So let's see properly here. So this is the graph for that. So f of x is equal to x. This is you can say displayed here, and since this point is not included, so we make it as a empty circle. And just to make a distinction between this one and this one, because once x is equal to 0, f of x is equal to 1. So we put it as a you can say filled circle, right? Filled circle. Again, if you look at, so what is the minimum? So what is the minimum for this function? Can we find?
No, I cannot.
Yeah, we cannot, because someone of you can think, we can think that, okay, the function value, you know because this point f of x is equal to 0, the function value is 1. Here, by the way, the function value is more. If, let's say, I consider this point, so for example point 4, so this one is even smaller value. So by definition, minimum means a smaller value. So we cannot find here again the minimum, but the infimum we can find. The infimum will be, because this function would approach 0. So the infimum, we can say yes, the infimum is 0. But if you ask what is the minimum, what is the minimizer, no, we can't find that, right? And we call it as a discontinuous function because there is a discontinuity. Like f of x is equal to x, this is all, as we approach x is equal to 0. But as we get to x is equal to 0, the function value gets to 1. So that is why, there is a discontinuity. We get all the way to this point, but at x is equal to 0, the function value gets to 1. So there is a discontinuity, and we just, give this kind of a function a special name, which is a discontinuous function or discontinuous objective. But the main thing is, again, that we can't find the minimum, but the infimum is helping us, right? and it's quite good enough, because if you look at if you keep only to the minimum, then you will not be able to find the minimum. But the infimum is, you can say, telling us about the problem, because overall if you see that the function value approaches 0, so the infimum is giving us a true picture, right? The infimum is giving us a true picture, and this is, I think, really helpful for sure, right? Because if you keep only to the minimum, then we can't solve this problem. So this is very interesting that, yeah, just to summarize, that all of the 5 examples, if you look at, okay, what does this mean, arg min? Anyone remembers arg min, what it means, what it refers to? Anyone? Arg min, what it means? So min means the minimizer or the minimum. Anyone?
Empty set.
Sorry?
It's the empty set.
Yes, but what it means, arg min? So what it refers to? Yeah, just make a guess, no problem. Arg min. So arg min means what? So arg min means, what do you think? What it could be?
It's when we
Arg min.
when we dealt with the feasible and unfeasible set.
Mm-hmm. No, no. So the min means minimum, right? Arg min means
Argument.
the meaning. Arg means, yes, it's the argument, but arg min, it means that what would give you the minimum, which means it is the minimizer. So once you see arg min, this means we are talking about the minimizer. And if we remove the arg, that means we are talking about the minimum. So for all the problems, the minimizer was not there. I mean, if you look at the minimizer, it was not there. So this is just like telling you, and if there is no minimizer, obviously there is no minimum. So you can say that the minimum was not, we can't find the minimum, and we can't find the minimizer. So this is arg min, just means that we are talking about the point which will give us the minimum. Now there is, I mean, a theorem which is there, that if you want to find a minimum and a minimizer, so I mean, let feasible set, right? S is a feasible set and it belongs to Rn, and it is closed and bounded. So that means it is closed and bounded. So we know that what are the bounds, and it is not like it should not be like discontinuous. It should be closed. So there is like some, you can say, it should be between some limits, and there should be some bound. Then we can say that the function, and the function is continuous. So the feasible set is closed and bounded. So there are like the upper bound, the lower bound, and it is not like it is closed. So there are some limits, and the function is continuous. If the function is continuous, then this problem, that we can, I mean, you can say we can find the minimum and the minimizer. So it is always, I mean, possible, or you can say the problem possesses a minimum and minimizer. Now, how to find the minimum and minimizer, that's a different story, and we would be talking about that later on. But the thing is, this problem, I mean, the objective has a minimum, and if there is a minimum, obviously there is a minimizer. Okay. So for example, if the function is non-continuous, then we can't say that the problem possesses a minimum, right? So we can't say like that. Now this is, yes, exactly the opposite. Now this slide is very interesting. Just okay. So this slide is very important because this helps us to see, I mean, the bigger picture again, that if somehow because throughout the course we would be talking about the minimum, we won't be, and the minimizer. We won't be talking about the maximum and the maximizer. So how to get from the minimum to the maximum is very simple. This equality is telling us that if we have got a function and we just take the negative of the function, right? So we just take the negative of the function and we apply the minimization problem. So we consider the negative of the function as a minimization problem. And at the end of the day, we again take the minimum. So this is just like taking the maximum. So that means, uh, we can consider, if we want to find the maximum, well, still, we can apply directly the minimization. The only thing we have to do is to take the function as negative, and then at the end of the day, we have to again make it negative. So this, equality helps us to see that the maximization problem can be used using the minimization approaches. Now, as I mentioned briefly before, this is just the other possible thing, that for the maximization problem we can have a similar problem, that sometimes we are not able to find the maximum, and the easiest example is f of x equals x, right? So if you see this line, do you know what is the maximum function value? No. But if I ask you what is the supremum, so your answer would be infinity, right? So we define this supremum as the least upper bound. So yeah, this is, I mean, one more difference, that for the supremum we say it's the least upper bound. So we say this is the least upper bound, and we can say that if the maximization problem is bounded above, so if we know that what is the bound, right, so we will say, okay, that value is the maximum, that value is supremum, so we can say that. And if it is unbounded, like in this case, so we say this is infinity. And yes, if the problem is infeasible, then we do just kind of a switch, okay, and we say that the supremum is minus infinity. It's just the opposite of the infimum. If you remember, for the infimum, if the problem was unbounded below, it was minus infinity, and here it was plus infinity. So just to keep the things in perspective, we are using plus infinity, we have to, and here we have to use, I mean, just a different thing, so we use minus infinity, right? So the supremum is equal to the maximum, right, of the maximization problem, if the maximum exists. If there is a maximum, then the supremum will be equal to the maximum. But again, coming to the question, the benefit of this supremum and infimum is that even if there is no minimum or maximum, I mean, the supremum could be found. The supremum could be found, in many cases. Even, if the problem is infeasible, we can say the supremum is minus infinity. So you can say that with these, functions, they are able to, cover, I mean, a lot of different kind of special cases. And even if, there is no maximum, or even if there is no minimum, well, the supremum can be found. Okay. Any questions?
Can we do anything with it? The supremum and infimum.
Yeah, so because yes, exactly. If you know that the problem is for example here, if it is bounded above, so if you know the upper bound, so in that case supremum equals the maximum, right? But if, for example, it is unbounded, we go towards infinity, even if the problem is infeasible, right? There is a problem in the constraint like we have seen, like the inconsistent constraints, the supremum will be minus infinity, right? So yes, it obviously, I mean, covers more types of functions, right? And more, you can say, situations. So more situations, they are covered in this kind of a function, right? Supremum and the infimum as well. Okay, now we just have some topics, left from this chapter before we really, start focusing on the uh, methods to solve unconstrained optimization problems. So, yeah, this one is just, I mean, a definition that we have got a feasible set. It belongs to Rn, and let's say the function is from the feasible set to the set of real numbers. And here we are just, saying that we are taking union of minus infinity to infinity. So we are taking into account these, this like infinity, and we have, uh, we have this belongs to R. So F refers to, so F steric, this always
Sorry,
refer
doctor.
to
But
the, yeah,
your
I
voice
think
was
there
cutting
is,
out.
okay, okay. So I continue. Yes. Okay. Excuse me. So the function, it's if you see like the first part, there is no difference. The only thing is, we are specifically, taking into account minus infinity and infinity, and we say that f steric. Yes, f steric is, it always indicates the minimum, right? It always indicates the minimum, just like x steric, it indicates the minimizer. So wherever you see x steric, this means this is the minimizer, and f of x steric, that means the function value at x steric. This is also written as f steric, and this means this is the minimum. Okay, so I've written it for you. So x steric, this means uh, the minimizer. F of x steric means the function value at the minimizer, which obviously means minimum. And sometimes, we write it like f steric, sometimes, but these two, they are the same. There is no difference between them, right? So here, I mean, it's just, we are saying that f steric is the minimum function value, and more, you can say, yeah, I mean, in reality, this means that there is some x steric, there is some point which belongs to the feasible set, and the function value at x steric is just given as f steric, and the last part, it sums up that the function value should be the smallest possible value. So it's a very easy thing. Let me draw, I mean, a surface, and then we will see. So if we have got this kind of a surface, so the minimum function value will be at this point. The minimum function value will be at this point, and we can say that this is the minimum, and this point could be termed as the minimizer. Now in this case, if we go in either direction, if we go in this direction or if we go in the other direction, what happens is that the function value would be more. The function value would be more than the function value here. So this will exactly, satisfy this inequality. So f of x steric will be less than f of x. So the function value at x steric, which is the minimizer. So this is the minimizer, and the minimum. So the function value at all other points would be greater than or equal to this thing, because it could be, we can have, I mean, something. Let me draw it for you. This is, I mean, a special case, and in this case, By the way, we have got, a set of minimizers. We have got a set of minimizers because the function value would be minimum at all these points, right? At all these points. So that is why, we are including less than or equal to. Okay, so here we are talking about less than equal to. Later on, we will see that what will be the impact. For the first one, we will say that this is strict minimizer. So we call this, okay, strict minimizer. Okay, minimizer. And for the other one, we can't say that this is strict minimizer. So here, and strict minimizer also means that this is unique. So here, for example, we have got a unique minimizer, but here we can't say that this is unique minimizer. Okay, just a okay, so we can have, here, for example, the unique minimizer, but here there is no unique minimizer. If you say at this point, at this point, at this point, all the points, the function value is the minimum. So we can't say that there is any unique minimizer. Okay, let's talk about, yeah, some algorithms. We will see that there are, two kinds of algorithms. The first one, which are direct. So direct algorithms means that we will directly get to the solution. So they seem really wonderful, but we would see there is a catch. And the other one, they are known as iterative. So in that case, we will get to the minimum because both of these algorithms, they could be used to solve minimization problem or maximization problem, right? The other type, which is iterative, that means we will get to the solution, we will get to the minimum, but in an iterative fashion. So we will get to the minimizer slowly, gradually. We won't be able to get directly. So in the first one, it's direct to the solution, and in the second one, it takes steps or iterations, or we also call it epochs, right? So we would take multiple epochs. Like for example, if you when you will study machine learning and these other courses, you will see that the algorithms, they are more like iterative algorithms. So more iterations are required, right? So for the time being, let's look at the direct algorithm. So direct algorithms, they seem wonderful that we can get to the solution, and that means great, right? So if you see the definition, it looks wonderful because there are a finite set of operations. So you just have to do a set of operations or set of instructions need to be followed, and you will get the solution. So you will get the solution which will be exact. So you follow the operations and you get the exact solution. But there is a problem. The problem is that these algorithms, they ask for too much, the direct algorithms. And what it means asking too much? We call them some unrealistic assumptions, because they say that all the numbers which are in the problem specification, they are represented in infinite precision. So for example, even if you are adding two numbers, just take a plus b. So in a plus b, well, and even like let's say a multiplied by b, for example. So in this case, you can say, first of all, a and b, they should be represented in infinite precision. Now you know that, infinite precision, well, it is unheard of. It is only, you can say, theoretically possible, but practically this is not possible, even with a supercomputer, right? So this is the first thing. So they are saying that, okay, at least the representation should be infinite, with infinite precision. Not only that, all the arithmetic operations, for example, if you add, if you multiply, whatever you do, if you divide, so the operations, they should take into account infinite precision. So this is again, asking for too much, and this is very difficult practically. And then
yeah, the operations should be carried out to infinite precision, and not only that, you know, even the answers to all the arithmetic operations are represented to infinite precision. So everything, you know, is infinite. So you can say that the direct algorithms, they look really great, but more, you can say, theoretically, from a theoretical perspective. But from, you know, from a practical perspective, they are not, you can say, very interesting. And then, I mean, if you follow all this, so for example, the numbers are with infinite precision, and you know, you are carrying out the operations, the arithmetic operations with infinite precision, then one thing is good, that you will get your answer as exact, right? So you will get your answer as exact, but you know, the cost which is associated with that, this is what we call exorbitant, which is too much, right? So in that case, practically this algorithm is not really helpful. So and you know, some problems cannot be solved by the direct algorithms. So sometimes, okay, let's say if you have integers, so you can apply direct algorithm, right? You can, if you have, for example, a is 4 and b is 3, so yes, you can add them, you can get your answer. But there are many problems, by the way, which cannot be solved by these kind of algorithms. And for example, if we have g, which is a function, set of real numbers to set of real numbers. So if, for example, we have got non-linear equations, like for example, if you have linear equations, the equations which we have solved, uh, we could, you know, solve that, and we could, I mean, even use a direct algorithm. Like you remember, we solve by two methods, which is the substitution. What is the other one? One method is substitution. Can you remember the other method? So if we have got a system of linear equations, how we can solve? Either by substitution, or what is the other
Elimination.
method? Sorry?
Elimination.
Yes, great, great. By the elimination method. So if, you know, for example, at that, it is direct. I mean, we will get a direct answer, and we will get a, you can say, exact answer, exact answer. But if, for example, we have got, let's say, you know, he's talking about like higher degree polynomials, like fifth, sixth. So there are more dimensions, and you know, things become really complicated in that case. So in that case, you know, there is no direct algorithm which exists, which can give us a solution. So you can say that if, for example, we have got fifth degree polynomial, so the maximum power is 5, right? For example, if we have any such thing like x raised to power 5, so you know, it is possible, certainly. And you know, as I have told you, that in the current era, I mean, it's very easy. So in that case, direct algorithm won't help us. So if direct algorithm won't help us, if there is no direct algorithm, then what we need to do, we need to go towards the indirect algorithm. In indirect algorithms, they are known as iterative algorithms. So they are, you know, you can say, much better, because they do not ask for infinite precision. They do not ask for that, right? So that's why, you know, they are good. But there is a catch, a slight catch, that mostly we'll talk about iterative algorithms, but mostly, you know, they won't give us an exact solution. They won't. Rather, they will give us an approximate solution. You cannot say that it will be exact, but it will give you approximate. Like even with a GPS, you know, you cannot consider that this is exact. Obviously, it is nowadays, you know, you can say very good, and it is to a certain meters, you know, it gives you an exact solution. But you can say it cannot be said exact. No, not exactly at that point. No, right? So still, you know, if you use GPS to get from point A to point B, so this is an example of approximate solution. It gives you a solution, yes, but we cannot call it as an exact one. It is an approximate one, right? Now, the iterative algorithms, as the name suggests, we have something, kind of recursion, or we have to repeat the algorithm again and again. So we have to repeat the algorithm, and this equation is a very common equation in computer science and in many other fields. So this is just simply, this is the new value. The new value is based on the old value plus blah blah. So there is something here. We will be talking about that, but there is like simple thing, new value depends on the old value. Now that means from the old value we can get to the new value, and that is why he's saying v is equal to 0, 1, 2. This is just the iteration counter. So the first time what would happen, x like v is equal to 0, it should be given to us, otherwise we can't start. So the first value it's given to us, and then from the first value we can get to the next value, and then to the next value, and so on. Things will continue. So if I put v is equal to 0, that means x of 1 would be equal to x of 0 plus something. Now what is the second part? We will come to that, but the first thing is, to start this algorithm you have to have an initial guess, because we want to get to this value, we want to get to the new value of x. But the first something like in the beginning we should have, right? We should have, because otherwise we cannot get to a new value. So you should have what we call as the initial guess. So there should be some initial guess, and there are like different, you can say, approaches for that. Sometimes it's just kind of a blind guess, sometimes it is more like an informed guess. Okay, so it all depends that what kind of problem we are solving. And xv is just the value of the iterate at the vth iteration. So for example, if I say the first iteration, so x of 1, so x of 1 here, it will be x of 1, that means the value at the first iteration. If I say x of 2, that means the value of x at the second iteration, and so on. Now here this is the additional thing. If this additional part is positive, what would happen? The value of x would increase, and if this value is negative, then the value of the current value of x would decrease. Okay, sometimes you also say this is the new value, this is the current value. The new value is dependent on the current value. Now here we have the step size, which is given by alpha. So alpha is the step size, and this just means that because this step size is multiplied by the change, right? This delta x is the change. We also call this as the step direction. So just imagine that if the step size is more, well, obviously the entire factor will be more, and there will be more change in x, right? There will be more change. But if, let's say, I decrease the value of alpha, then what would happen? The the impact on the current value will be less. No, okay, then the step size is normally between 0 and 1, but it is not equal to 0. So what will be the problem if I put equal to 0? If I put alpha equals to 0, what would be the problem?
We will not get anywhere. It's the same value.
Exactly. Yes, it will remain where it is. Great, great. Because if alpha is 0, that means entire factor is 0. That means there won't be any change. And we want some change, right? We want some change. And the algorithms are designed in such a way that in the first iterations, this is more for most of the algorithms. In the first iterations, the algorithms, they do not really work well. But gradually, slowly, things will improve, right? So that is why, but the thing is, there should be some change. If there is no change, then there is no benefit. So that is why, alpha is always greater than 0. And normally, the step size, we do not want to make it too much. So we put an upper limit, which is 1. But it can be equal to 1. It can be equal to 1. There is no problem in that. But normally, the alpha is between 0 and 1. So for example, 0.5, 0.8, something like that. Okay, then there is one more thing. If if you see here, this is R plus. So R, we have seen R includes all set of real numbers. Okay. If you put this plus, so what it means that this is, I mean, 0 is not in, so negative numbers are not included, right? So if you put R plus, that means 0 is not included, right? So just to remove the 0, because 0 is not possible now, so we put it like R plus, right? Now there is a slight change in the notation later on, because most probably, yeah, I think there's a mistake here, because normally there is what happened. We'll see in the next slides that there is, I mean, R plus and R plus plus. But maybe at this point, since it is introducing the introduction and the notation, so it's not very specific. But in general, if you have set of real numbers, like there's no plus, there is nothing, so that means negative, positive, everything is there. If you put 1 plus, that means negative numbers, they are out of question, but 0 is possible. If you put 2 plus, then 0 is also not possible. So this thing is more like, using this thing, because 0 is not possible. If you put 0, it won't make sense. Anyways, for the time being, we can just say this delta x, this is a step direction. Now this is a step direction, the delta x, because what happens is it can be positive. If it is positive, the impact will be positive. If this is negative, the impact will be negative. So if delta x is positive, that means the value would increase, maybe by 0.5, 0.2, right? If let's say alpha is 1 and delta x is 0.5, so that means we will increase the value. But if alpha is 1 and if delta x is minus 0.5, then the value will decrease. So this, just tells us that the value would increase or decrease. Okay, then we have to see that, yeah, this product, which is like alpha multiplied by delta x, we say that this is the update, because this value is effectively added in the current value. So we call this second part as the update. So if you see here, I mean, graphically, we are trying to show that this is xv. So the old value, this is the new value, xv plus 1. The old value plus the update gets us to the new value. Okay, the old value plus the update, this all is update. And what is update? Update is alpha delta x, right? And the step direction is given by delta x. Now just imagine that if the direction is opposite, then what would happen? You will not go in this direction, but rather you will go in the other direction, right? Then if I make it, negative, then it will be in the opposite direction. If I just make it minus, I multiply with minus, so the direction will change. So that is why, that determining the direction also is very important. Once we get to the minimum, I mean, in these algorithms, you have to see that the direction should be good enough. Because if the direction is not good enough, well, we won't get to the minimum, but rather we will get away from it. And we'll see, there is, I mean, in these algorithms, there is always a chance that rather than going towards the minimum, if we make just one mistake, that, we do not take into account the step direction, we can get to the maximizer. We want to get to the minimizer, but somehow we can get to the maximizer. Okay. So I think we'll stop here, but this, update, this is very much, there in machine learning. For example, if you look at the perceptron, I mean, it's one of the algorithm, but the perceptron update, try to just, Google this, and you will see that, this is very close to this. And for many other algorithms, in machine learning, like we have, for example, the passive aggressive algorithms. They're also very interesting algorithms. So we do talk about, these updates, right? So we will talk about that, but the main thing is just to conclude the lecture, that direct algorithms, they are very good. They give you exact solution, but they are asking for too much. They're asking for infinite precision, which is like only possible theoretically. For the iterative algorithms, they are not asking for anything like infinite precision, but mostly they will get you to an approximate solution, right? They will get you to an approximate solution, and most of the time it is all good, even for the driverless cars. I mean, if we get approximate solution, that is good enough, right? We do not want to be like exact, but we just want to, for example, be safe, and we should just take care of the other people, and the other traffic, the pedestrians on the road. But even if we get something, approximate, it is not, kind of a problem. But as of now, still, it is in development phase. It is there. I mean, it is being developed for the last 20 years, even more than that, and it is still, not, you can say, and you can say it's not there for everyone. So it's still in development phase, because even with getting, I mean, an approximate, or what we say, acceptable solution, I mean, it's not an easy task. So I would stop here, and if you have any questions, please, you can ask.
Thank you very much, Dr.
It's my pleasure. It's my pleasure. Thank you so much. Most welcome. So I would be here. Okay.